Okay, welcome to Chapter 16, Section 2, Nature of Light. So, key ideas. How do scientific models describe light? What does the electromagnetic spectrum consist of? And so let's get started here with it. How do scientific models describe light? The two most common models describe light as either a wave or as a stream of particles. Light produces interference patterns as waves do. Light can be modeled as a wave. This model describes light as a transverse wave, which is what we saw earlier, the oscillating electric and magnetic fields that don't require a medium or a material in which to travel. Light waves are also called electromagnetic waves. They consist of changing electric and magnetic fields, just like we talk about. Wave model of light explains how light waves interfere with one another, why light waves may reflect, why they refract, and why they diffract. So, the wave model of light cannot explain some observations though. When light strikes a piece of metal, electrons fly off the metal surface. This is something called the photoelectric effect. Light can be modeled as streams of particles, so like energy packets. So in the particle model of light, the energy of light is contained in packets called photons. A photon is basically a unit or a quantum of light. It's kind of basically like a big ball of energy of light. So a beam of light is considered to be a stream of photons, and photons are considered particles. They don't have a mass. The energy that they have is located in a specific area. And so you can see here, as far as the wave model and the particle model, they explain some of the things that happens with light: reflection, refraction, diffraction, interference, and the photoelectric effect. So one model explains part and the other model explains the other parts. So let's watch this little video here.
Although our knowledge of waves and particles has greatly contributed to our understanding of light, neither a wave model nor a particle model fully describes the nature of light. Light exhibits characteristics of both particles and waves. Light reflects off a mirror the way a ball bounces off the ground or sound bounces off the walls of an auditorium. And when light passes from one medium to another, it refracts, as will both sound waves and physical objects. Unlike particles and physical objects, however, waves can pass through each other, occupying the same space at the same time. Like sound and other types of waves, light diffracts or bends when it comes to an opening that is the same size or smaller than its wavelength. In addition, light experiences constructive and destructive interference, a phenomenon unique to waves. Yet wave behavior does not explain why light above a certain frequency is able to excite electrons in a piece of metal. If light were simply a wave, then any frequency of light should work, provided that the intensity of the light was great enough. A particle, or packet, on the other hand, would have an amount of energy associated with it, an amount that either was or was not great enough to excite an electron. So with respect to the photoelectric effect, light behaves as a particle. Both the wave model and particle model offer valid insight into the nature of light. Sometimes it is easier to think of light as a bunch of small particles called photons, and sometimes it is easier to think of light like waves on a pond.
Okay, so the model of light used depends on the situation, as you can see. So the dual nature of light can behave both as a wave and as particles. So the energy of light is proportional to frequency. The amount of energy in a photon is proportional to the frequency of the corresponding electric wave. So you can see here some types of waves. You have infrared, visible light, and ultraviolet light. The wavelengths, very long wavelengths for infrared, shorter and then shorter for ultraviolet. The frequency goes from a low frequency to a high frequency, from infrared to ultraviolet. So the photon energy goes up and is more intense in ultraviolet than in infrared. That's why you get a sunburn from ultraviolet radiation, not from visible light or infrared. So, the energy of a photon.
The energy of a photon is equal to the product of Planck's constant times the frequency of the photon. 93.7 megahertz is a common radio broadcast frequency. If we substitute 93.7 megahertz into the equation, we get the energy of the photon. This equation can be looked at differently by using the relation. The frequency of the photon is equal to the speed of light divided by the wavelength. This means that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength of the photon. Blue light has a shorter wavelength than red light. From this relation, we can determine that blue light is more energetic than red light.
If you've ever seen a flame, the blue flame is always a hotter region than the red flame, and it seems like that would be a weird thing, that seemed like blue would be cooler. But bluer inside a flame, the blue part of the flame is always a more energetic, a higher heat than the red light. So the shorter the wavelength that you go, the more energy is contained in the electromagnetic wave or in the light wave. So the speed of light depends on the medium. In a vacuum, here you see that it travels at almost 3 times 10 to the 8th meters per second. In air, it's roughly the same thing. In ice, it goes down a little bit. As you go down to diamond here, the speed's about cut in half, or actually a little bit more than half. Although it's still traveling at 1.24 times 10 to the 8th meters per second, so it's still an incredibly fast speed. So the brightness of light depends on its intensity. The quantity that measures the amount of light illuminating a surface is called intensity. Intensity is the rate at which energy flows through a given area of space. And intensity depends on the number of photons per second, or the power that pass through a certain area of space. So here, a kind of a diagram. As you go away from the sun, if you take or say some kind of light, here not in the sun, but some kind of light at 1 meter away, you take a square and you have a certain amount of energy that goes through that. Well, that same amount of energy that passed through that square gets separated at 2 meters, gets into fourths. So the energy that was in it at 1 meter is spread over 4 times the area at 2 meters, and then over 9 times the area at 3 meters. So the intensity goes down the further away that you get from the source of light. So what does the electromagnetic spectrum consist of? The electromagnetic spectrum consists of light at all possible energies, frequencies, and wavelengths. The visible spectrum is only a small part of the electromagnetic spectrum, and each part of the electromagnetic spectrum has its unique properties. So let's look here at the different parts of the electromagnetic spectrum.
Electromagnetic spectrum. Electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. Visible light, X-rays, microwaves, and radio waves are all forms of electromagnetic radiation. Together, all the forms of electromagnetic radiation form the electromagnetic spectrum.
Okay, so here you have the electromagnetic spectrum. You have decreasing wavelength, which means the wavelength is getting shorter and shorter and shorter as it goes from left to right. You can see that by the purple squiggly lines there. But they do increase in frequency. The shorter the wavelength you get, the more waves can pass you every second, or more waves can be generated per second, which increases the frequency. And when you get down here to gamma rays are what comes generally out of nuclear reactions. They're very high energy. They will cause serious damage to human tissue. X-rays are also fairly high energy. They can cause damage to human tissue, That's why they limit the exposure. It's not nearly as much as what gamma rays would do, but they will penetrate through your skin and tissue, and they have a harder time, will kind of bounce off of bones. That's why they're used to look at your bones. Ultraviolet just means beyond violet. It's just a section of the sun. This is where you get your sunburns, is from ultraviolet light. Visible light, which is what you see, all the colors. And remember, all of this is all electromagnetic radiation. All these forms are radiation. They're just at different energies. Visible light is radiation, but it's radiation that doesn't hurt you. Infrared means it's below red. Microwaves, which are fairly long wavelengths, they affect water molecules in your food, and that's how it actually cooks your food. Is it the microwaves energize the water molecules and heat those up, turn them into steam, which heats your food, not the actual microwaves themselves. Then you have radio waves that broadcast television and radio stations. So radio waves are used in communications and radar. They have wavelengths that range from tenths of a meter to thousands of meters long, usually fairly long. Radar, which is radio detection and ranging, a system that uses reflected radio waves to determine velocity, very similar to sonar, except that it uses radio waves instead of sound waves. Microwaves are used in cooking, have wavelengths in the range of centimeters. Infrared is, you can feel as warmth. Those are slightly longer than red visible light. Sunlight contains ultraviolet light. Ultraviolet light is a portion of the UV spectrum. X-rays and gamma rays are used generally in medicines. X-rays have wavelengths that are less than 10 to the negative 8th meters. They're very small. And gamma rays are electromagnetic waves with the highest